Hi, everyone. Welcome to this first talk for 2023. It is my pleasure to welcome Nicolas Klein, which we used to be a researcher for a long time in Canada and is now back to European soil in Paris too. He's a specialist of dynamic games and questions related to information in microeconomics. And today we'll present a joint work with Chantal Marla and Lucie Ménager on information acquisition. The floor is yours. You have 1 hour.
Okay, so thank you very much for having me here, and thank you to everyone for connecting, and Happy New Year, of course, to everyone. Yeah. So so this is a world premiere. Yeah, so please, I'm very much looking forward to your comments and suggestions. So this is joint work with my new colleagues at Paris 2, Chantal Marla and Lucie Ménager, and our topic is objects in the rear view mirror, information acquisition with payoff, rivalries, and observation lags. Yeah. Okay, so what are we after here? Yeah. So I guess already the title is reasonably descriptive. Yeah. So we're after a situation where there is both an informational externality, a positive informational externality among players, and a negative payoff externality. Yeah. So more specifically, yeah, so we have a sequence of short-lived agents who are uncertain about the quality of some technology or about the feasibility of an innovation, yeah, and each one of them wants to be the first to achieve a breakthrough, yeah, or to achieve a success with this new technology. Yeah, so there's it's like a classical R&D race. Yeah, so there is this payoff rivalry that's going on. Yeah. At the same time, they learn from their predecessors' experiences with the technology. Yeah, so there is a positive informational externality in that other players' efforts help a player make better decisions. Yeah. Yeah, and they use this information in a Bayesian way. Yeah, yeah. Okay. Yeah. So there's this negative payoff externality versus the positive informational externality, and now our well, the possibly innovative part of this project is that players observe the results of previous efforts with some exogenous delay. Yeah, yeah, and well, so I guess if you think of some classical examples that are that may be used to motivate these informational externalities or strategic experimentation settings. Yeah, delay presumably plays some role. Yeah, so if you think of farmers trying out a new crop, well, some time elapses between sowing the seed and then observing the yield that you get. Yeah, or researchers who try out a new research avenue. Yeah, well, some time elapses between writing the paper and then getting the letter from the editor telling us what he thinks about it. Yeah, or patent races for drugs and vaccines. Well, some time elapses between the administration of the drug or the vaccine and the effect or the lack of an effect, as the case may be. Yeah, and so we're interested in understanding how this delay impacts or modifies the dynamics of information acquisition. Yeah. Okay. So we're connecting to several strands of literature, and well, the literature review is still very much under construction. So this is a very incomplete list, yeah. But so I just give you 4 strands of literature where we think we're connecting to, yeah. Yes, so one strand would be, the strategic experimentation literature, which is arguably, or which might be one of the canonical means of approaching problems of informational externalities, yeah, of positive informational externalities. Now, the list of papers here is very incomplete, yeah. So I've regrouped them by bullet points according to what is observable. Yeah. So in the first bullet point, everything is observable. Actions and outcomes are observable. Yeah. In the second bullet point, actions are unobservable. Outcomes are observable. Well, so here in Marlatz and Ménager, it's costly to observe the other players. Yes, so you incur a cost. In the third bullet point, actions are observable. Sorry, but outcomes are not. Yeah. But of course, we're far from the first to introduce a payoff externality into this setting. Yeah. So here again, so the list is extremely incomplete. Yeah. So for instance, in Moscarini and Squintani, they look at an R&D race where players initially observe some private signal about the quality of some some investment project, yeah, and players it's a stopping problem, yeah. So players decide when irreversibly to invest, yeah, yeah, and of course in the incomplete, very incomplete list, I've included my own paper, yes, so with Kausaftas, where we look at the impact of various patent regimes on incentives for information acquisition, yeah. In an extension, we're comparing 2 settings, so in that sense, we're connecting to the contest design literature. And here for the 4th bullet point, to the best of my knowledge, the list is complete. Yeah, yeah. So there is one paper by Gordon, Marlatz, and Ménager that introduces observation lags in a classical strategic experimentation setting, that is with a pure payoff, with a pure informational externality. Okay. And so in that paper, the assumption is that I observe the results of my own experimentation right away, but I observe the results of others' experimentation with some delay. Yeah. Yeah. Okay. And they get effort cycles in equilibrium. Yeah. So by contrast, so what we're doing here is the following. So we have short-lived agents. We have a positive informational externality and a negative payoff externality, and we have observation lags. And in an extension, we compare 2 settings. Yes, so that's the connection to the 3rd point here. Okay. Okay, then maybe let's turn to the model if you want. Yeah. So time is continuous. There is a continuum of short-lived players that are indexed by the time at which they live, or at which they make a decision. Yeah. What decision does each player make? Well, each player is endowed with one unit of a resource, which he or she can invest in a risky technology or not. Yeah. So the marginal cost of investing the resource is some constant, some strictly positive constant alpha. Yeah. Okay. Now, this risky technology can be good or bad. Its quality does not vary over time. Yeah? If it is bad, it never gives any payoff. Now, if it is good, it gives a payoff of 1 at the time t plus capital delta. Yeah, so where capital delta is a parameter. Yeah, which corresponds to the exogenous observation lag. Yeah, so it yields a payoff of 1 at time t plus delta, if and only if a first success is produced at time t. Yeah, yeah. So what is a first success? Well, it's simply a jump. So if the first jump in a Poisson process occurs at time t, well, so this Poisson process has a rate of or a parameter of lambda, which is scaled at instant t with the investment at instant t. You know? Lambda is greater than alpha, and alpha is greater than 0. You know? So let's just assume that the game ends when the first payoff has occurred. We have a common prior that the technology is good. Yeah, so let's call it P0. Actions and payoffs, when they are realized, are perfectly observable. Yeah, yeah. So actions are immediately observable, and the payoff is observed when it realized. So if it's produced at time t, it's observed at time t plus delta. Yeah. And so far, we don't have discounting in our model. Yeah, so since players act only once, yeah, maybe discounting is superfluous. Yeah, so far, no discounting. Yeah. Okay. Okay. So, how do we update beliefs? Yeah. Yeah. So, yes. Sorry.
Please. May I ask a clarifying question, or shall
please do. Yeah.
Please, if you could go to the previous slide. Yes, so here you have the condition that the limit when tau goes to t is 0. Do you mean that we assume that there are no successes before time t?
That's right. Yes. So only the first success gives a payoff. Yeah. Yeah. So I want to be the first to patent the drug, let's say. Yeah. Yeah. And once I've patented it, well, that's too bad for the others. Yeah. So I've won the race. Yeah.
Okay. Yeah. And where do you encode the dependency of being the first successful tester and the investment, or is it still to come?
Yes. So if I understood the question correctly, it's encoded here. Yeah. In the fact that
right. Yeah,
that the Poisson rate is scaled with the intensity of investment.
Right. Thanks. I didn't know that.
Thank you. Oh, okay. So, okay.
Thanks.
Okay. Any further questions? Okay. Thank you. Okay, then let's turn to the updating. So before time capital delta, well, I don't observe anything informative about the technology, right? Right. So before time delta, my belief will be at p0. Yeah. So I don't get any useful information until time delta. Yeah. After time delta, yeah, of course, if no success has been observed yet, yeah, so because if a success has been observed, the game is over anyway, yeah. So after time delta, what is my belief that the technology is good? Yeah, it's equal to my prior belief p0 that the technology is good times the probability of my not having observed a success conditionally on the technology being good, of my not having observed a success until time t. Yeah, yeah, okay, okay, okay. Yeah, so note that this depends on efforts between time 0 and time t minus delta only. Yeah, okay. Yeah, so this divided by the same term plus initial probability that the technology is bad, 1 minus p0, times the probability that I don't observe anything conditionally on it being bad, which is 1. Yeah, okay. Okay, and we can write this in differential form, and so we see that beliefs can only go down over time. Yeah, yeah. So as time progresses and I don't observe a success, well, I get more pessimistic about the technology, weakly more pessimistic. Yeah, yeah. Okay. All right. So now, what is a player T's expected payoff? Yeah. Well, so his expected payoff is linear in his choice variable KT. Yeah. So where KT is the fraction of his unit endowment that he devotes to the risky technology. Yeah. Yeah. So if he invests in the risky technology, well, he incurs a cost of alpha. Yeah. And then he gets an expected benefit, which we write lambda times mu t. Yeah, so why do we write it that way? Well, it's so that all the dynamics are in this variable mu t. And now what is this mu t? Now this mu t is the product of two probabilities. Yeah. First, the probability pt. Yeah. So my probability assessment at time t that the technology is good. Yeah. Yeah. Times this exponential factor. Yeah. So what is this? So this is the probability that I have not been preempted by a success that I haven't observed yet, conditionally on the technology being good. Yeah, yeah, yeah. So the danger for me at time t is that one of my predecessors has already gotten the results that allow him to take out a patent. Yeah, and then my investment would be wasted. Yeah, yeah. So this exponential is the probability that this has not happened. Yeah. So it's the probability that I have not been preempted by a success that has not been observed yet, conditionally on the technology being good. Yeah. Yeah. And so you see the two externalities I talked about in the motivation or in the introduction. Yeah, you see in these two factors. Yeah, yeah. So you have the positive informational externality in the PT, and then the payoff rivalry or the negative payoff externality in the in the exponential. Yeah. Okay. Okay, so we can compute the law of motion. Yes, so just the derivative with respect to time of this mu t, and well, so this gives us this expression. Yeah, and I will refer back to this equation a lot in what will follow. Yeah, yeah. So in principle, this can go either way. Yeah, yeah. Okay, can go up or down over time. Yeah. Okay. Okay. Yeah. So what's in green in my slides are just reminders of previous equations. Yeah. Yeah. So yeah. So what is player T's best response? Well, his objective is linear in his choice variable. Yeah. Yeah, kt, yeah. So if mu t is larger than alpha by lambda, yeah, so which we call p lower bar, well, he should invest his entire endowment. If mu t is strictly less than alpha by lambda, well, he should not invest. Yeah? And if mu t is equal to alpha by lambda, anything is a best response. Yeah, and what will determine the exact fraction that player T will devote to the risky technology will be the need to keep future generations indifferent. Yeah. So it will be given by the equation mu dot equals 0. Yeah, and this is what will generate our dynamics. Yeah. Okay.
May I ask once more, please? So what you mean is that what you said that we are going to determine the exact fraction needed to keep the future indifferent. You mean that that is the condition for an equilibrium, right?
Yes, yes. So at least for an equilibrium such that there exists a time path, a well-defined time path of mu. Yeah, yeah.
Right. Okay.
Which we require for admissibility. So I have not shown you this, but yes. Yeah.
Okay. Thanks.
Exactly. Thanks. All right. Okay. All right. So yeah. So let's look at what the equilibrium looks like. Yeah. So first, well, let me start off with the most uninteresting case. Yeah. So if we start out below this Marshallian threshold, let's say alpha by lambda. Yeah. So if P naught equals mu naught less than weakly less than P lower bar, well, then no one will ever invest. Yeah. Mu T will be below P lower bar for all T. And yeah, that's the equilibrium. Yeah. Not very interesting, but I mention it for completeness. Yeah. Okay. So now let's assume that we start out above this P lower bar. Yeah. So let's assume that P naught equal mu naught is strictly larger than P lower bar. Okay. Then everyone will invest fully in the risky technology up until some finite time tau. Yeah, yeah, yeah. So where tau is the first time at which mu hits this P lower bar. Okay, okay. After time tau, yeah. So at time tau, mu hits P lower bar. Yeah. So then after time tau, the investment is such that future generations are indifferent as well. Yeah, so that mu stays at P lower bar, yeah, or equivalently that mu dot equals 0, yeah, and that just means that the intensity of investment at instant t, yeah, is this linear function of the investment at time t minus delta, yeah, where the factor of proportionality, if you want, is just the belief at time t times this indicator function that indicates that we're after time delta. Okay. So now what does this translate to in terms of dynamics? Yeah. Yeah, so so for that, let's make a case distinction and distinguish the case tau greater than delta from the case tau less than delta. Yeah, okay. So let's first assume that tau is greater or equal than delta, which is the case if and only if p naught, yeah, so our initial prior is large enough, yeah, in particular larger than p lower bar times e to the power of lambda times delta, yeah. So this just means that it takes mu longer than delta to decrease to p lower bar, given that everyone invests fully, you know. Okay, so then what happens in this case? Yeah. So before time tau, everyone invests fully. Yeah. So that's how we defined tau. After time tau, well, we're after time delta as well. Yeah. So the indicator function is switched on. Yeah. So after time delta, after time tau, the investment intensity at time t is just this linear function of the investment at time t minus delta, yeah, where the factor of proportionality is the current belief at time t, yeah. Note that this implies a downward jump at time tau, yeah. Yeah, so coming from the left to time tau, the investment is 1. At time tau, we jump down to p tau, yeah, strictly less than 1. Yeah, yeah, okay. And by virtue of this formula, yeah, so this downward jump replicates indefinitely, yeah. So what we have is a monotonically decreasing investment intensity, yeah, so which is discontinuous, yeah, and so which has jump discontinuities at time tau, tau plus delta, tau plus 2 delta, etc. Yeah. And this just economically, this just comes from the need to keep future generations indifferent. Yeah. The further we go into the future, the less optimistic these generations are about the quality of the technology. Yeah. 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 So to keep them indifferent, well, I need to reassure them that that the threat of preemption is low. Yeah, yeah, yeah. Yeah. So that at least conditionally on the technology being good, they're not very likely to be preempted. Yeah, yeah. Okay. In the limit, well, so these jump sizes go to 0. Yeah. And the experimentation intensity goes to 0, yeah. The belief PT tends to the threshold alpha by lambda, but these limits are never attained in finite time, yeah, yeah. Okay, so here I also have graph that I didn't manage to include in my PDF for some reason. Yeah. Okay. but here it is. Yes. So this red line indicates delta. Yeah. And the green line indicate the jumping times. Yeah. So the first here is at tau, then at tau plus delta, tau plus 2 delta, etc. Yeah. Up until time tau, everyone invests fully. Yeah. Then at time tau, we jump down to p tau. Yeah, so then the investment rate decreases continuously. Then we jump down again at tau plus 2 delta, decrease continuously, jump down again, decrease continuously, etc. Yeah, and in the limit we tend to 0. Yes. So what else could? The curvature of these continuous bits is well, for these parameters, it's first concave, yeah, then it turns to convex, yeah. Yeah, for other parameters, it can be convex throughout, yeah, so these are the two possibilities, yeah. Okay, so, yes, so that's for this optimistic case, yeah, where P naught is large, yeah. Okay. So now let's look at the case at which tau is strictly less than delta, yeah. Yeah. So we hit indifference, yeah. So mu hits this P lower bar at a time that comes before time delta, yeah. So this is the case if and only if a P naught is in between this P lower bar and P wiggle. Okay. Okay, so then what happens? Yeah, yeah. So before time tau, again, by definition of time tau, everyone invests fully. Yeah. Now, tau, by assumption, is less than delta. Yeah. So this indicator function is switched off. Yeah. Yeah. So we hit indifference before time delta to maintain indifference. Yeah. So we need, we then need k equal to 0 in between time tau and time delta. Yeah. Yeah. At time delta, the indicator function is switched on. Yeah. And so for times after time delta, we again have the same formula as before. Yeah. So the investment intensity at time t is a linear function of the investment intensity at time t minus delta. Yeah. So it's that multiplied by the belief. Yeah. 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 So now note that we have two jumps on this interval 0 to delta. We have a jump down to 0 at time tau, yeah, and the jump up again to P delta equal P naught, yeah, at time delta, yeah, yeah. And so these two jumps, so one downward jump, one upward jump, yeah, yeah. And so these two jumps replicate indefinitely again, yeah, by virtue of this formula, yeah. Yeah, so now we have a non-monotonic investment rates, yeah, yeah, which jump down to 0 at time tau, tau plus delta, tau plus 2 delta, and then jump up again, yeah, at time delta, 2 delta, 3 delta, etc. Yeah, yeah. Again, the jump sizes tend to 0. Yeah, yeah, yeah. So yeah. So here I've written it for the upward jump. Yeah, yeah. So the size of the upward jump is strictly decreasing over time. Yeah, and it tends to 0, but never attains 0 in finite time. Yeah. Okay.
Nicolas,
Yes.
do you? I don't manage. I got some intuition of why it jumped down, but do you have an intuition why it jumped up again?
Mm-hmm. Well, maybe not a very good one, but it's all due to the need to keep future generations indifferent. Yeah, yeah, yeah. So if I didn't jump up again at time delta, yeah. So the generation just after time delta would say, okay, the probability that it's good is still P naught. Yeah, yeah, because during the first delta periods, I don't learn anything about the technology. Yeah, yeah. And then if my predecessors have if my predecessors had not jumped up again with their investment rate, I would say, well, now I strictly prefer to invest, yeah, because conditionally on the technology being good, I'm very unlikely, yeah, to be preempted. So let's try, yeah, yeah, yeah. And then this same story replicates every delta periods, as it were, yeah, yeah, yeah. But of course, the further I go into the future, the more pessimistic I am about the quality of the technology. Yeah, yeah, which implies that the upward jump gets smaller and smaller. Yeah, yeah.
Thanks.
So that's yeah, yeah. That's the intuition we have so far. So maybe yeah.
Okay, thanks.
Uh, Thank you. Yeah, but so recall that the belief that the technology is good is decreasing over time. Yeah, monotonely decreasing. Yeah, so it either stays fixed, stays constant. Yeah, or it strictly decreases. Yeah, yeah. So this means that yeah, more pessimistic generations may experiment more. Yeah, yeah, because they are more optimistic about not being preempted. Yeah, yeah. So we're still. So if someone has an idea of a good example, yes. So we're still looking for an example of this kind of dynamic, yeah, where let's say a particular research avenue is first pursued, then abandoned for a while, then taken up again at a lower intensity, then abandoned after a while, taken up again, etc. Yeah, yeah. Our story being that you have these two effects. Yeah. So on the one hand, you get more pessimistic over time, of course, monotonely more pessimistic over time that this particular avenue might lead to something. But at the same time, if no one has pursued this avenue for a while, yeah, it kind of becomes a high risk, high yield investment. Yeah, in the sense that if it's good, well, I have a pretty good chance of being the first of making a breakthrough with this. Yeah, yeah. But yeah. Yeah, and so in the limit, we again tend to the belief alpha by lambda, but never reach it in finite time. Yeah, and so the graph for this case, yeah, looks as follows. Yeah, so again, the red line is delta, period delta. Yeah, so up until time tau, well, we invest our full resource, then we jump down to zero, stay at zero till time delta. At time delta, we jump up to P naught, decrease continuously till tau plus delta, jump down to zero, stay at zero, jump up again, decrease continuously, jump down, etc. Yeah, and the jump sizes get smaller and smaller, yeah, and vanish only in the limit. Yeah. Yes. So what I said before about the curvature of the continuous bits applies here as well. But yeah, so I admit that you don't see it very well. Yeah. So it's first concave, then convex. Yeah. Or it could for other parameters it's convex throughout. Yeah.
Nicola, can I ask something?
Yeah.
But on each segment, it is either concave or convex, right? It's not.
No, there can be one segment where there's the inflection point.
Ah, I see. It can be inside.
Yeah.
Okay.
I think
I
here
wasn't
in
sure.
the optimistic case, well, yeah, okay, so the inflection point could be somewhere here, but yes, no, the inflection point can be in one of these continuous bits. Yeah, that we haven't ruled out. Yeah. Okay. 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 So if there are no further questions, yeah, we can look at payoffs, which are much better behaved. Yeah, so they're continuous and monotone. Yeah, so decreasing over time. Yeah, so well, in the if we start out pessimistic, well, no one ever invests, so everyone will get a payoff of 0. In the case of intermediate priors, yeah, after time tau or starting at time tau, we're indifferent between investing and not investing. Yeah, so our payoff is that from not investing, so 0. Yeah, before time tau, well, payoffs are strictly positive and decreasing in time. And yeah, so this is what could show, or well, you can see right away that this is continuous at time tau. Yeah, so if you plug in for tau, you get 0. Yeah, for t equals tau. Yeah. Okay, so it's decreasing, continuous and decreasing. Yeah, so the same is true for optimistic prior beliefs. Yeah, so after time tau, we're indifferent, so we get 0. Before time tau, well, we get something strictly positive and strictly decreasing in time. And yeah, so now you don't see it right away, but this is continuous as well. Yeah. Yeah, so of course it's not very surprising that payoffs should be decreasing over time. Yeah, because as time progresses, we become less and less optimistic about the technology. Yeah, and yeah, so other things being equal, the threat of preemption increases with time. Yeah, so think of player 0. Player 0 is certain not to be preempted. Yeah, yeah. Whereas later players can be preempted. Yeah, so we have these two effects that go in the same direction. So we have decreasing. Yeah, so decreasing payoffs. Yeah. Okay. Then let me show you, well, at least one comparative static, and try to give you an intuition for it. Namely, the comparative static in the length of the observation lag. Yeah, so in delta. Yes, and so note that what interests a player, or what interests player T when he computes his best response, is only what happened before time T. Yeah, yeah. Okay, so and now suppose we're in this intermediate case. Yeah, yeah. So provided we stay in this intermediate case, time tau is independent of delta. Yeah, yeah. Right. Because what happens before time tau is just that everyone will play, will invest fully independently of delta. Yeah, yeah, yeah. So after time tau, everyone gets zero anyway. So their payoffs are independent of delta anyway. Yeah. Now, given that time tau is independent of delta, everyone's also every player who moves before time tau has a utility that is independent of delta. Yeah. Yeah. So as long as we're in this intermediate case, nothing depends on delta. Yeah. Yeah. Nothing depends on the observation lag. Yeah. Yeah. Okay. Now, if we're in the optimistic case, yeah, yeah. So that being defined as the case where the first moment of indifference is larger than delta. Yeah. Yeah. If we're in this case, what happens before time delta, yeah, is again independent of delta. Yeah. 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 So everyone will fully invest. Yeah, independently of delta. So payoffs of these players will be independent of delta. For players that move in between delta and time tau, however, yes, so the threat of preemption or the probability of being preempted increases with delta, meaning that their utility will decrease. Yeah, yeah. The probability of preemption increasing also implies that mu t will be decreasing, implying that tau will decrease in this case. Okay, okay, okay. Then yeah. So maybe just briefly some asymptotics. Well, so those I've mentioned already. Yeah. So the belief, if we start out above this Marshallian threshold alpha by lambda, yeah, yeah. So our beliefs, so the belief tends to this threshold alpha by lambda, but never reaches it in finite time. Yeah, yeah. Well, for any belief below 1, yeah, so the investment will converge to 0 in the limit. Yeah. Okay. We can also compute well, what is called, or what is sometimes called the amount of experimentation. Yeah. Yeah, so which is simply the sum, or the integral rather, of investments in the risky technology. Yeah, yeah. So one can compute this and note that this does not depend on delta. Yeah, yeah. So the amount of experimentation, or the probability of eventually getting a success conditionally on the technology being good is independent of the observation lag delta. Yeah, yeah. So in that sense, in the very long run, the observation lag doesn't matter. Yeah, yeah. Okay. So let's call this amount of experimentation TW. W for winner takes all, because I'll refer back to this in the next section. Yeah.
Yeah, I've got a question. Have you got some intuition as to why this probability is not is independent of capital delta?
Okay, so
So imagine that you need
Yeah.
more so you get the results.
yeah.
Why?
Okay, so why is that? So this follows from the fact that the limit belief is always this Marshallian threshold. Yeah, yeah. So in the very long run, we just go on.
I think we lost the speaker.
Yes, so do I.
Yeah, maybe we wait. It might be just internet connection that is fragile.
Sorry. Yeah, so what I feared happened. Yeah. Sorry. Okay, so I'm back. Okay, good. Thanks. So the question was, what's the intuition for why this amount of experimentation does not depend on delta? Yeah. So I'm not sure it's I have a very good intuition. Yeah, but the reason is simply that as long as P times lambda is still strictly greater than alpha, yeah, so there is some some force pushing me toward investing, yeah, because yeah, so the instantaneous, or forgetting about a preemption, yeah. Yes, so the instantaneous return from investing is larger than the cost of investing. Yeah. So suppose no one has invested for delta periods. Yeah, as long as P is strictly larger than alpha by lambda, I have an incentive to invest. Yeah. No matter what delta is. Yeah. Yeah, so there is this force that in the long run makes us pursue this this technology until we hit this this belief P lower bar. Yeah.
Okay.
And this force is there independently of delta. Yeah, so it might just take a very long time. Yeah, but in the long run, this is what gives us the fact that the amount of experimentation is independent of delta. Yeah. Okay. Yeah. So I suppose I have 5 minutes. Yeah. Okay. Yeah. So then let me just tell you briefly that we're comparing this winner takes all mechanism, yeah. So or setting, yeah, which I just presented, with what we or what is called hidden equal sharing mechanism. Yeah. So where the idea is as follows. Yeah. There is some principle who observes all the breakthroughs that are being produced. Yeah? Of course, he observes them with a delay of delta. Yeah, and that keeps them secret until some deadline, T wiggle. Then he reveals them, and everyone who has had a success by the time T wiggle gets an equal share of the profit of one. Yeah, yeah. Okay, okay. So that's the idea. And this now also works if actions are unobservable. Yeah. Okay. So just some observations. Yeah. So if I live within, or if I need to make a choice within delta periods of the time t wiggle, yeah, of course, there's no point in my investing, so I will not invest. Yeah. Now, if I live, so the real deadline is then this capital T equal t wiggle minus delta. Yeah. If I live, sorry. If I live before time, a capital T, well, we can compute my expected reward conditionally on my having a success. Okay. Okay. So just by noting that if n other players have a success, I get 1 over n plus 1. Yeah. Yeah. And then this gives us then a nice formula thanks to the Poisson assumption, yeah, for my expected reward, sorry, conditionally on my having a success. Note that this does not depend on the lowercase t. Okay, so at the time I'm actually living, it just depends on the time capital T, yeah, on the deadline via the amount of experimentation that will be performed up until that deadline between time 0 and time t. Okay. Also note that since successes are hidden, yeah, beliefs don't move. Yeah. Okay. Yeah, and then it's very simple to compute a player's best response. Yeah, so a player should invest if lambda times pt equal p naught times the reward is larger than alpha, not invest otherwise. Yeah. Okay, and so I guess I have 1 minute left. Yeah. Yeah, so with that, one can show that essentially the optimal deadline, optimal in the sense of both maximizing the probability of an innovation and minimizing the expected time of the innovation arriving, would be one where I set the deadline equal to TH plus delta, where TH is the amount of experimentation such that the player is just indifferent. Okay, and then yeah, and then we can give a necessary and sufficient condition for the amount of experimentation to be higher under this equal sharing mechanism than under the winner takes all setting. Okay, and I suppose so it's 4 o'clock, so I should stop. Yeah.
Thanks, Nicolas.
Thank you for.
There were already a few questions during the talk. Are there more questions?
Yeah, I've got one more question, if I may. But perhaps someone would ask before me. I've asked several questions already.
No, please feel free.
My question is, if I want to model possible predictions of what the results are going to be, and can it be modeled? Probably not, but I just have this idea of modeling that with the same model, but the capital delta being negative, so that I know the results with a certain probability before the experiment, because of some inside information or industrial espionage or something like that. But I think that the model as is won't work as if you just take the delta negative, right?
I haven't thought about this at all. I would presume not, because so what would this mean? Yeah, so this would mean that at the time I decide whether to invest or not, I know if so at the time when I decide whether to write the paper, I know if my paper will be accepted or not. Yeah, because
Probability, like not with probability 1, but you
Yeah.
know the no, but you know, sorry, I meant you know whether the results will be positive or negative. Delta it was about the results, not about being preempted.
Exactly. But if I knew my result to be, if I knew that my paper is going to be rejected, I'm not going to write it.
Yeah.
If I know that it's going to be accepted, I will write it. Yeah.
Even if you have, but if you face the risk of preemption, then I think
Yeah. Okay.
like being scooped by someone else that can
Yeah.
make.
Okay, so then I would need a second delta, right? Which kind of captures this risk of preemption, right? So I would yes, no, okay. So thinking about it for 10 seconds, my answer would be probably you would need a second parameter in that model that still captures the preemption threat somehow. Yeah. So I know that my paper is such that it would be accepted if no one else has submitted a similar paper before me. Yeah. And that I don't know, right? If someone yes.
I mean, I think that in certain areas it is kind of clear that some work is important. The question is who makes it first.
Okay.
My intuition, not that I'm sure of that. And as for the question is how you can, but yeah, you're right. You need to extend the model to make it to model that.
To model this preemption aspect how but to say something more sensible, I think I need to think more about it, but I think it's an intriguing idea to take this delta less than 0 and then a model preemption or the threat of preemption in some other way.
Yeah, like physicists often do that. They just think of some positive value, and then at some point it turns out that if they take this negative, then it works as well or something. Yeah, then. Okay.
Yeah, thank you.
I realize it's beyond the idea of the model. I'm just
Yeah, thank you.
Any other question? Okay, so if not, let's thanks Nicolas.
Yeah, thank you. Thank you, and Happy New Year. Oops, sorry.
I lost the button that stops the recording because I had some issues here. So
Oh, so